Hello everyone, this is Haodong from Southwest University of China. Today I will present our work, which is about DRAM cache management with request granularity for NAND-based SSDs. This presentation has 5 parts. Let's start with the introduction part. NAND-based SSDs show better performance on random access, power consumption, and massive parallelism compared with hard drivers, and have been widely used in digital devices, data centers, and high-performance computers. The figure shows the typical architecture of modern NAND-based SSDs. As shown in the figure, the DRAM is deployed between the host interface logic and the flash memory. Besides storing the mapping table to support address translation, the DRAM is commonly used to buffer rest data of user applications. When a request is delivered to the SSD from the HIL interface, the flash translation layer services the request with the faster DRAM, so that the IO latency can be significantly shortened. Once the DRAM cache becomes full, with the buffered data, the cache management schemes need to evict code data pages to make room for newly written data. So the cache management scheme that determines whether data is cold or hot imposes relentless impacts on the cache efficiency. The next part is the background and motivation. I will introduce the background and our motivations in this part. Cache management inside SSDs. Cache inside SSDs can absorb certain I/O requests to avoid forwarding them onto the underlying flash array, which in turn improves SSD performance. Cache management mainly focuses on the replacement strategy to make room for newly written data by evicting some of the previously buffered data. Most traditional cache management approaches inside SSDs, such as LRU, CFLRU, and their variations, manage the cached data at the page granularity that corresponds to the basic read or write unit of the flash array. The page-based methods can identify the locality of each data page and consequently improve the cache hit ratio. But they fail to explore the spatial locality across multi-pages in the DRAM cache. Considering the garbage collection process of SSDs is performed at the unit of a block, the block-based cache management schemes have been proposed to exploit spatial locality of data pages belonging to the same block. Block-based cache management groups in-cache data pages into a cluster corresponding to the same logic block. After that, both adjustment and eviction operations of cached pages are performed in the cluster granularity. However, managing the cached data in the block granularity may directly impact the efficiency of the DRAM cache of SSDs. This is because each cached block contains dozens of pages, including both cold and hot data pages. In I/O workloads of real-world applications, some write requests commonly involve higher temporal locality than those with larger write requests. That is to say, the access frequency of the data page may be related to the sizes of its write request. Figure shows the results of page hits and page inserts as CDF according to the size of the request. In the figure, request size means the size of write request, whose contents are inserted to the DRAM cache. The CDF result of page height implies the proportion of page height on the pages whose write request size is equal to or less than the corresponding request size to all page heights. Similarly, the CDF result of page insert represents the portion of inserted pages whose request size is equal to or less than the corresponding request size to all pages inserted to the cache. Taking the trace of HM1 as the example, we see that the requests whose size are no more than 20 KB insert less than 20% of the pages to the cache, but contribute more than 80% of the page hits. Similarly, in the other cases, pages of small requests contribute a major part of cache hits, while large requests insert more pages to the cache. Furthermore, we exploit how many cache data pages of large size requests are hit in the cache. And the figure represents the results as shown. Only 20% and 37% of cache data pages of large requests have been reaccessed. That is to say, only a small part of buffered data pages of large size write requests will be reaccessed in the cache. Such observations motivate us to design a request set-based cache management approach to not only assign a higher priority for the cached data pages associated with the small size requests, but also abstract the how to access the data from large write requests and keep them separately in the cache. Then, let me show you our design of our approach. We propose a DRAM cache management scheme with write request granularity for NAND-based SSDs called IQ block. The principal idea of IQ block is taking a request block as a basic unit for cache space allocation and adopting different routines for cache request block management with small and large size write requests. As shown in the figure, when a write request arrives, we build a request block by grouping its data pages and initially insert it to the head of inserted request list. Then, IQ block supports upgrading the cached request blocks to the higher level linked list of small request lists and divided request lists, where they or part of them are hid in the cache. Specifically, we configure a set limit delta for the page number of the request block in SRL. And the request blocks that have more than delta data pages can't be directly moved to SRL. They must be split first and inserted to the divided request list. Once the cache becomes full, IQ block compares the priorities of the tail nodes of 3 linked lists and evicts the request block that has the lowest priority for making available cache space. Here is an example of our approach. As shown, the request block are initially inserted to the inserted request block. For the page hits on large request block, we might make page upgradation for the hit pages. Assuming that page R plus 1, R plus 2 are hit by a request, we build a new request block in the DRL and move the hit pages to the new request block. And it is similar for the adjustment of page hits on page K plus 1 and K plus 2. Besides, the divided request blocks in DRL may still be large request blocks. For the pit heads, we make another split for the request blocks. When a page of small request block are hit in the cache, IEQ block adjusts it with an upgradation operations and directly moves the hit small request block to the head of small request block. Assuming that the page k plus 1 is hit, we move the request block to the small request block. Similarly, we make the same adjustment for the pit hit on page k plus 1. To the end, we introduce the victim selection for Pdeviction according to the access frequency. The victim request block is chosen from the tail node of 3 linked lists, and the request block with the lowest access frequency will be selected. Equation defines the access frequency of request block, and a tail request block with the smallest value will be evicted, where the access count is the access count of the block. Bit number is the number of hits in the request block. T current and T insert are the current time point and the insert point of the request block. To the end, the request block with the lowest access frequency will be evicted. Furthermore, request IEQ block supports downgraded merging of cached blocks and evicts them in batch. And the figure demonstrates the workflow. As seen, the tail node of DRL is selected and to be evicted as it has the least value of access frequency. Then we will merge it with its original request block in the lower level list of IRL by referring to spatial locality and evict them together in batch. We have carried out certain tests to evaluate the proposed approach. We implement our proposal in the SSD simulator. In this paper, the DRAM cache is set to 16, 32, and 64 MB. To make a comprehensive assignment of IQ block, we select 6 commonly used disk traces that are collected from different kinds of applications. Especially the LUN1 is recently collected from the VDI, and the remainder 5 traces are selected from the block I/O trace collection of MSRC. Apart from widely used LRU algorithm, we also take the VBBMS and BPLRU into comparison evolution. BPLRU supports block-level LRU replacement, and the cached block can be adjusted to the tail of the LRU list for the preferential eviction, while it is written sequentially. VBBMS splits the cache space into a random request service region and a sequential request service region by following the proportion of the 3:2 and adopts the virtual block as the cache management granularity. In the IEQ block scheme, the size limit of the request block in small request list is a sensitivity parameter, which is used to distinguish small and large request blocks. From the results of our sensitive tests, as shown in the figure, we conclude that the delta value is 5, results a better kit ratio and I/O performance for most of the selected I/O workloads. Thus, we use this value by default in our evolution. I/O response time is the primary indicator of performance in SSDs. The figure shows the normalized result of I/O response time after replying the selected traces. We can see that IEQ block can make a significant reduction on I/O response time. Specifically, IEQ block can reduce I/O response time by 14.3% on average compared to the selected cache schemes. VBBMS and IEQ block result in better I/O performance with the selected I/O traces in contrast to LRU. That is because VBBMS and IEQ block performed cache eviction with a virtual block or request block granularity that contains several data pages, which exploits the multi-channels inside SSDs. BPLRU generally performs worse than VBBMS and IEQ block, though it also manages the cached data with the block granularity. The reason is that BPLRU flushes the whole block consisting of many data pages onto a single SSD block, which fails to utilize access parallels across multi-channels inside SSDs, and then affects I/O performance. We argue that the optimization of I/O response time is related to not only the cache hit ratio, but also the utilization of multiple channels in the context of SSDs. The term of cache hit means the ratio of the pages from I/O request that is absorbed by the cache without accessing to underlying flash memory. A higher cache hit ratio implies less access to underlying flash areas, which contributes to better I/O performance. IEQ block can improve the cache hit ratio by 23.5 on average. That is the first reason of better I/O performance of IEQ block. The next reason is the batch eviction. To characterize the eviction in the four cache management schemes, we record the number of ejected pages in each eviction operation. As shown in the figure, IEQ block evicts 4 to 13 pages in each eviction process on average, which contributes to better I/O performance. BPLRU, BBMS, and IEQ block eject multiple data pages in each eviction. That means the data pages are flushed to the flash memory in batch, and more cache space can be freed up for upcoming write requests. However, this may increase the number of write operations to the flash memory if the flushed data pages are updated in the near future. So we recorded the write count after running the selected benchmarks by using different cache management schemes. As reported in the figure, IEQ block causes the least number of write count in most traces. More exactly, IEQ block can reduce the flash writes by 4.7 on average. Our proposal of IEQ block preferentially ejects code large request blocks, as the data pages of these request blocks are less likely to be updated frequently. On the other hand, IEQ block can then hold more hot data pages in cache to observe write requests and thus yield better performance. The time overhead of IEQ block is mainly caused by moving the items of linked lists corresponding to the cached data pages and the pre-calculation, the priority for cache eviction, and both of them can implemented with the time complexity of O1. In other words, the runtime overhead of REQ block is acceptable. The space overhead is due to storing the linked list, which is directly related to the number of cached items and the set of list nodes that corresponding to the cache item. The figure shows the space overhead of selected cache management schemes. As seen, our proposal of REQ block needs 67.6 KB and 133.6 KB and 271.6 KB on average with different sizes of cache configuration and corresponds to an average of 0.41% of total cache space. Finally, let me make a brief summary about this work. We present a novel cache management approach to separate hot and cold buffered data for SSDs called REQ block. REQ block can enhance the cache efficiency by taking the request size of cached pages into account. Experimental results illustrate the number of cache hits can be improved by 23.5% on average, and then the error response time can be reduced by 40.3% on average. Thanks for your time.